Then to mitigate bottom-standing porous structure. Bottom-standing porous structure. Gagan, please share your screen.
Yes, sir. I'm sharing my screens. Sir, my screen is visible, sir.
Scanning. We need a few seconds. Yes. Okay.
Yes. Okay. Sir, shall I start, sir?
Yes, please start.
Yeah. Yes. Okay. Hello, everyone. My name is Gagan Sahoo. Currently, I am pursuing my PhD degree at Department of Mathematics, Indian Institute of Technology, Ropar, India. So, the title of my talk is Mitigation of Hydrodynamics Responses of Water Wave on Elastic Plate in the Presence of a Bottom-Standing Porous Structure. This is my combined work with my senior Dr. Sophia Singla and my supervisor Dr. Subhash Chandra Martha. So this is the content of my talk. An introduction, I'll explain some basic of water waves theory. Then literature surveys related to CIs, that is by modeling as a thin elastic plate. Then my current research problem, followed by the conclusion and references. So as you can see in the figure, the when wave is propagating in the presence of a obstacle, the some of the wave energy is reflected by the obstacle and some of the wave energy is transmitted below the obstacle. So nowadays many researchers are interested in studying the surface wave interaction with the elastic plate. So these are some literature surveys. So as you can see in the year 2001, Sahu and others have studied the scattering of water waves by a semi-infinite elastic plate by using the Fourier transform method. So as you can see, this elastic plate is a semi-infinite elastic plate. So the computational burden is very high. So to reduce this computational burden, in 2003, Enterburn and Hermans have considered the finite very large floating structure. So as you can see, this structure, these elastic plates are open to the high wave load, so which can damage this structure. So in the year 2018, Singla et al. Studied that in the interaction of water waves by a elastic plate in the presence of porous barrier, and they have studied how this porous barrier can affect can reduce the wave load on the elastic plate. So by motivated by this study, we have considered we are interested here to the surface wave interaction with the elastic plate in the presence of a bottom standing porous structure. So this is my this is my model problem, that is as we can see in the figure 4, the elastic plate is kept the porous structure is kept at a distance L1 from the elastic plate, and to solve this problem we have considered certain assumption, that is fluid is incompressible and inviscid and flow is irrotational, and we have considered here linearized water wave theory, and we have considered here that wave motion is simple harmonic in time. So by considering this example, and if the angle is the angle of incident of the wave is at an angle theta, then the real potential phi can be expressed as equation 1. And following the corresponding boundary value problem will reduce that, that is the governing equation will given by equation 2. Due to the flat bottom, a rigid flat bottom, the bottom condition in the region 1, 3, 4, 5, 6 will be given by equation 3, and the free surface condition, that is the combined kinematic and dynamic condition, is given by equation 4, where mu is equal to k0 sine theta and capital K is equal is omega square by g, where this k0 is corresponding to the incident wave number. So, as here we have the condition on the plate will be given by equation 5, and here we have considered that the elastic plate is free to move, so which is the free edge condition in the both the end will be given by equation 6, and the far field condition which is given by equation 7 and 8 respectively. So here, as due to the presence of elastic plate and porous structure, here the whole domain of fluid domain is divided into 6 regions. So due to the continuity of velocity and pressure, the matching condition in each interfaces, that is between 1 to 1 3 2 4 2 3 4 and 4 5 and 5 6 reason, the matching condition will be given by equation 9 to 22, where your m is the inertial coefficient and f is the frictional coefficient, and epsilon p is the porosity of the porous structure. So to solve this problem, we have used here the eigenfunction expansion method. So after applying the separation of variable in the governing equation, which is a reduced wave equation, the potential that will be in the region 1 will be given by 23, in region 2 is given by 24, in region 3 is given by 25, and region 4 it is given by 26, and region 5 given by 27, and region 6 is given by 28. Here the psi n, mn, pn and gn are the eigenfunction, and rn, gn, hn, bn, cn, dn, en and tn are the unknown constant, and here the R0 and T0 are corresponding to the reflection coefficient and transmission coefficient respectively. So these are the eigenfunction expansion expression, that is psi n, mn and qn, fn are given by this expression, and g is nothing but epsilon p by m plus if, and the term knx, pnx and alpha nx is given by equation 30. So here the kn, pn and alpha n are the roots of the dispersion relation, that is equation 31, which is corresponding to the open water region, equation 32 which is the corresponding to the porous region, and equation 33 which is the corresponding to the elastic plate region. So after truncating the infinite series into n terms, we'll get, and by using the by using the matching condition, we'll get a linear algebraic system of size 12n plus 12, which is solved numerically to find the unknowns r naught and t naught. So to validate the present model, we have in, as we can see in the figure 5a, in the absence, when the porous structure is absent, the our problem is corresponding to the Herman 2003 papers is work. So and we have found that the numerical results are well matched, and similarly in the absence of elastic plate, that is the interaction of water waves by a bottom standing porous structure, which is the work by the Lasoda et al, and we have found that our result are well matched with the Lasoda and other works. So now let me go to the result section. So in figure 6 figure 6 is the free surface elevation and plate deflection for different values of length of the elastic plate, frictional coefficient, length of the porous structure, frictional coefficient of the porous structure and porosity of the porous structure. So in figure 6a we can see, as the length of the porous structure is increasing, the free surface elevation in the free surface elevation as well as the plate deflection is decreasing. And similarly here in figure 6b and 6c also we can see, as the frictional coefficient and porosity of the porous structure is increasing, the free surface elevation as well as the plate deflection is decreasing. This may be due to, as the porous structure length or frictional coefficient and porosity is increasing, more wave energy dissipated by the porous structure and less wave is transmitted towards the elastic plate. And similarly, in figure 7, this is the graph for shear force and strain for different A by H. So in figure 7 also we can 7A and 7B we can see as the length of the porous structure is increasing, shear force and strain of the elastic plate is decreasing. So next result is figure 8. As you can see in the figure 8, this is the reflection coefficient, transmission coefficient, and dissipation coefficient versus the distance between the elastic plate and distance between the porous structure and elastic plate for different value of length of the porous structure. So as we can see in the figure, the reflection coefficient, transmission coefficient, and dissipation coefficient follows a periodic and oscillatory pattern with respect to the L1 by H. And it also noticed that as the length of the porous structure is increasing, the dissipation coefficient is increasing and transmission coefficient is decreasing. In figure 9, we can see similarly in as observed in figure 8, the figure 9 so that the reflection coefficient, transmission coefficient, and dissipation coefficient follows an oscillatory periodic pattern, and it also noted that as the porosity of the porous structure is increasing, the the more wave are dissipated by the porous structure and less wave are reflected and transmitted. So in the figure 10, it is a reflection coefficient, transmission coefficient, and dissipation coefficient versus the angle of incident for different value of frictional coefficient. So as we can see in the figure, so in between 0 to 30 degree, the reflection coefficient and transmission coefficient and dissipation coefficient follows a oscillatory pattern, but in the near to theta equal to 22 degree, there is a sharp rise in the deflection coefficient, reflection coefficient, and a sharp decrease in the transmission coefficient. And it also noted that as the frictional coefficient is increasing, the reflection coefficient is decreasing and transmission coefficient is decreasing, but the frictional coefficient is increasing. As we have observed in the figure 7 and 6a, 7 and 6b. So here we have observed that plate deflection is decreasing and shear force and strain is decreasing. So in figure 11, so this is the reflection coefficient, transmission coefficient, and dissipation coefficient versus the length of the elastic plate for different value of flexural rigidity of the elastic plate. So here also we observe that the reflection coefficient, transmission coefficient, and dissipation coefficient follows an oscillatory pattern with respect to the L2 by H. And it also noted that as the flexural rigidity of the elastic plate is increasing, the formation of nodes and antinodes are decreasing, and the as the flexural rigidity is increasing, the rigidity of the elastic plate is increasing, so more wave are reflected by the elastic plate. So here is the conclusion. So here the boundary value problem is solved by the eigenfunction expansion method, and using the boundary value problem is solved by numerically to find the coefficient, that is reflection coefficient, transmission coefficient, energy dissipation coefficient, free surface elevation, plate deflection, and shear force and strain. And all graphs shows that the reflection coefficient, transmission coefficient, and dissipation coefficient are follows a oscillatory and periodic pattern in with respect to L1 by H and L2 by H, and the free surface elevation and plate deflection decreases in the with the increase in porosity, length and frictional coefficient of the porous structure, and shear force and strain decrease with an increase in length of the porous structure, and At last, we have observed that reflection coefficient and transmission coefficient decrease with an increase in length, porosity, and frictional coefficient of the porous structure, and the reverse pattern is observed for energy dissipation coefficient. So these are my references. For at first, I would like to acknowledge the Council of Scientific and Industrial Research, Government of India for financial support to pursue my PhD degree, and in IIT Ropar for providing all the necessary facility. Thank you.
Thank you very much. Any question, please?
Gagan, could you please go to slide number 13?
Yes, sir. Yes, sir. Slide. Yes, sir.
Yeah.
Sorry.
It has not come yet. Yeah. Your incident wave is from left to right.
Yes, sir.
And
That is minus 32 from left to right. The incident wave is coming, sir.
and which region corresponds to your this porous breakwater?
Sir, this is from 0 to 20, sir. Here the porous structure is there.
Okay, there is some decay. Okay.
And sir, this region is corresponding to the region between elastic plate and porous structure.
In that region is there any to and fro motion, back and forth motion? Because
Yes, sir, definitely due to the as elastic plate is there, elastic plate will reflect some wave, sir. So here some reflection of wave by elastic plate will be present here, sir.
okay. Can you go to slide 14?
Yes, sir.
Yeah. What is your L2?
Sir, L2 is the length of the elastic plate, sir. Sir, L2 it is
So if
in the
L2, okay, L2 is the length of the elastic. Okay. If there is no plate, still you have some reflection because of the structure. Okay, thank you.
yes.
Thank you.
Okay.
Question?
No, Mike has no question.
Any question, please?
Yes, sir. Sorry, sir.
Any question, please?
No, not for you. No.
If there is no question, we can complete this session. And I thank you, everybody.